If you turn around at the edge of a black hole, you'll see 100 versions of yourself. This isn't magic. It's the work of a mind-bending region called the photon sphere, where light itself gets trapped, endlessly circling the black hole. Just 15 seconds later, even light won't be able to escape your line of sight. Today, we're diving into something extraordinary. What would really happen if you fell into a black hole? This isn't science fiction. It's a deep, serious thought experiment grounded in hardcore physics. But before we plunge in, let's get one thing straight. What exactly is a black hole? Even Einstein, yes, that Einstein, once described black holes as where God divided by zero. He didn't even believe they could actually exist in nature. And yet, we found them. When supermassive, ultra-dense stars die, they go through a radical transformation. They collapse entirely under their own gravity, leaving nothing behind. What remains is called a singularity, a point in the fabric of space and time with gravity so intense that it's essentially infinite. Einstein's general theory of relativity changed everything. It told us that gravity isn't some invisible force pulling objects. It's space and time bent and warped by mass. This explains why Earth orbits the sun and why the planets move as they do. Inside a black hole, there's no solid surface. The singularity within is just that, incredibly dense. It warps space-time so violently that it forms a deep well, a kind of cosmic pit with vertical walls. Back in 1939, Einstein published a paper saying that such collapses into singularities shouldn't happen, that they were mathematically possible but physically unrealistic. Ironically, that same year, J. Robert Oppenheimer, yes, that Oppenheimer, and physicist Hartland Snyder released a paper saying the opposite. A star absolutely could collapse into a black hole under its own gravitational pull. So let's revisit our big question. What happens if you get thrown into a black hole? Here's the wild part. Anything can become a black hole. A star, a planet, even you. All it takes is compressing matter into a small enough space, the so-called Schwarzschild radius. German physicist Karl Schwarzschild was the first to find an exact solution to Einstein's equations. His result, both stunningly simple and powerful. If the sun were squeezed into a sphere just 3 kilometers wide, it would become a black hole. Earth, compress it down to about 9 millimeters, the size of a marble, and boom, black hole. And a human? You'd need to be crushed into something smaller than a proton. Almost unimaginable. But if you could pull it off, you too would become a black hole. So which black hole are we choosing for this ride? A small one? Too boring. Let's go big. Some black holes are so massive, their event horizons are larger than our entire solar system. They weigh billions of times more than the sun, but maybe that's overkill. Let's go with something a bit closer. Sagittarius A star, the supermassive black hole at the center of our Milky Way. You're already orbiting it, by the way. So is everything else in our galaxy. It's one of only 2 black holes that humanity has ever managed to photograph directly. Let's set the scene. You and I board a spaceship and fly towards Sagittarius A star. We park 1 trillion meters from its event horizon. Time to begin the descent. You go in, I stay back. From the ship, I watch as you begin your free fall. Here's the twist. Time behaves very strangely near a black hole. General relativity tells us that the closer you get, the more space-time bends, and the more time distorts. You'll carry a special watch showing 2 time zones, your time and mine, back on the ship. We sync our clocks, and you begin your journey. Almost immediately, you witness something stunning. Matter spiraling into the black hole, glowing hot. The friction heats it to insane temperatures, making it shine intensely. To simulate this on a regular computer would take over a decade of processing. In real life, the light would appear bluish-white, but simulations often color it orange for visibility. First time check, 30 minutes have passed for you. You've traveled just 0.1% of the way. Meanwhile, I've experienced just 11 seconds more than you. So far, not too dramatic. But as you get closer, space-time bends more intensely. Light from beside or even behind the black hole bends around toward your eyes. Visual distortions begin to stack up. Time check again. 2 hours in, you've covered just 1.4% of the distance. I'm now 44 seconds ahead. You also notice the black hole's shadow growing faster than expected. That's due to gravitational lensing. Light that would have missed you is now bent straight into your eyes. More time passes, you check your watch again. From your perspective, it's been 12 hours. From mine, I've been watching you fall for 15.5 hours. Now, you're on the edge. Things are about to get very weird. Just before the point of no return, you pass through the photon sphere, a surreal, mysterious boundary. If you could somehow freeze time and look around, you'd see something incredible. A place where light orbits the black hole in circles. This isn't reflected or emitted light. This is pure light, trapped in orbit. If a photon's path is perfectly tangent to the curvature, it can orbit forever. But a tiny deviation sends it falling in or flying out. Here, if you turned around, you'd see the back of your own head, and dozens of copies of it. Real-time reflections of yourself. No mirrors, no tech, just space and time bent into a loop. Continuing forward, you pass the photon sphere. The black hole now fills your vision. It feels like total darkness is swallowing you. But this isn't normal darkness. It's light bent so violently that even the back and sides of the black hole's shadow are visible at once. You've now been falling for 13 hours. Only 24 minutes remain. From the ship, I've been watching for 20 hours. Another 18 minutes pass. Now my clock says I've been watching you for 40 hours. Your final 18 minutes equal 18 hours for me. And then, the moment arrives. 6 minutes left. You take a breath. Glance at the watch. It looks broken. It says I've been watching you fall for infinity. But it's not broken. That's just physics. From my perspective, I'd spend decades watching you slowly approach the event horizon. Eventually, I'd only see you via infrared, your light stretched and redshifted beyond human vision. I'd never actually see you cross the threshold. Even if I lived forever, that moment would stay forever out of reach. For you, it's 6 final minutes. For me, it's eternity. It sounds like fantasy, a surreal dream, but it's completely real. Einstein's equations predicted all of it. Now you're inside the event horizon. Surprisingly, you wouldn't notice anything at first. You'd still see the stars. You might even see the spaceship. But all that light, like you, is being pulled toward the singularity. You've crossed the point of no return, a realm where physics breaks down, time stops. Escape would require faster-than-light travel. Not happening. Some believe that from inside, you could see the entire future of the universe flash before you. But that's a myth. Instead, the outside universe would shrink into a thin ring of light, faint, ghostly, fading. And then comes the finale. You get close to the singularity. Your feet stretch forward, your body pulls apart like pasta, a process called spaghettification. You're torn atom by atom until you become one with the black hole, a speck, floating in eternal darkness. Chilling, isn't it? And yet, you can't help but wonder. Black holes, they terrify us, they fascinate us. They are the edge of reality.